This video is Chapter 9, Part 2, a continuation of Mendelian genetics. First is the law of independent assortment. That law states that during meiosis, chromosomes line up randomly at the equator of the cell. And because of that, alleles of different traits are not always inherited together. Meaning, just because, let's say, I'm looking at a mouse that is brown with a long tail, it does not necessarily mean that all of the brown offspring will also have a long tail. It's the idea that fur color and tail length are inherited separately due to the fact that they are on different chromosomes. So independent assortment means that they line up differently during meiosis. There's two possible combinations that these red and blue chromosomes can line up in. As you can see, that then produces different combinations that can be in the offspring. So law of independent assortment says that traits do not always just automatically travel together. Each trait is inherited separately. This diagram shows you how two traits can be inherited separately or independently from one another. In both of these crosses, we start with the same set of parents, yellow and round, crossed with green and wrinkled, and the offspring produced out of those Punnett squares are all yellow and round but heterozygous. When I am looking at two traits, such as round wrinkled, that's one trait, and yellow-green, that's the second trait. When I am looking at more than one trait, my Punnett squares get much larger, and that's because of independent assortment. I can't assume that big letters will always travel together or that round automatically means the P will be green. No, everything is inherited separately. Here's a few practice questions. I would recommend you pause, try them on your own, and then listen to the explanations. In lions, long whiskers is dominant to short. Black feet is dominant to brown. I have a particular lioness. That's her genotype. What's the chance that her egg will contain big H, little b? I'm first going to look at big H. What is the chance of her passing on big H? Well, she only has big H, so 2 out of the 2 alleles that she passes on will be big H. What is the chance of her passing on little b? Well, she's got a 50-50 chance because she could pass on big B or she could pass on little b. So she has a 1 out of 2 chance that she will pass on little b. When I multiply these fractions, that's what I'm going to do. Statistics tells me the chance of 2 separate events occurring is a multiplication event. When I multiply, I just go straight across the top. 2 times 1 is 2. On the bottom, 2 times 2 is 4. Gives me a fraction of 2 out of 4. I can simplify that to a half. Question number 2. I've got brown eyes and black eyes also added into the picture, and I have my male here. I want to figure out the chance of his sperm containing this combination. So I'll go through each letter separately. The chance of sperm containing big H is a 50-50 shot because he could pass on big H or he could pass on little h. The chance of him passing on big B is again 50-50 shot. He's got a big B and he's got a little b, so the chance of passing on a big B is a half. Next, little e, the chance of him passing on little e, well, he only has little e. So the chance of that occurring is 2 out of 2. Or I could write that as 1 out of 1 because we know 2 out of 2, 1 out of 1, that's the same thing. So whichever one is great. Then I'm going to multiply on the top. 1 times 1 is 1, times 2 is 2. And on the bottom, 2 times 2 is 4. 4 times 2 is 8. So I have a 1 out of 4 chance that that's what he's going to pass on. Continuing to look at more than one trait at a time, I have an idea of a dihybrid cross. When you see questions that involve a dihybrid cross, you have 2 options. Option number 1 is shown on the left, which is to draw a giant table. In order to draw that giant table, I need to figure out all of the possibilities that come from parent number 1 and all of the possibilities that come from parent number 2. So in order to find these letters up at the top, I look at parent number 1. Parent number 1 has to give an A and a B to the offspring. So that parent could give big A, big B, which is there. That parent could give big A, little b, which is here. That parent could give little a, big B, which is here. Or little a, little b, which is here. So I have my 4 possible combinations from parent 1 across the top. On the left, I have the combinations from parent 2. Parent 2 could give big A, big B, which is there. Big A, little b, which is here. Little a, little b, little a, big B, which is here. Or little a, little b, which is here. So I have now set up my Punnett square, and of course once it's set up it's quite simple to fill in the squares. The problem is setting it up. So once I have it set up, I can then fill in the squares and see my offspring. A different option, if you don't like that approach, is to use multiplication. My personal preference is that I prefer multiplication. It's easier in my brain to understand, but you, of course, should do what's easier in your brain to understand. If I'm doing multiplication, I'm again going to set up a cross of each letter separately, like some good old-fashioned Punnett squares like we were doing in video 1. So for A, I have these 2 possibilities, so I'm going to draw that Punnett square here. And for B's, I would also draw a Punnett square. And then I would multiply my results. Generally, all these dihybrid questions are about phenotypes, so I'm now ready to multiply my results. I want to see how many are dominant, how many are going to be dominant recessive, how many will be recessive dominant, and how many will be recessive recessive. So those are my 4 options of what the offspring could phenotypically look like. So I'm just going to multiply my fractions to find that. Here I see that 3 out of 4 are big A, meaning 1 out of 4 are little a, and I'll multiply those by my B's. I see that 3 out of 4 are big B, meaning 1 out of 4 are little b, and then I can multiply to solve. 3 times 3 is 9 out of 16. 3 times 1 is 3 out of 16. 1 times 3 is 3 out of 16. And 1 times 1 is 1 out of 16. So these are my ratios of what the offspring would look like. I see those same ratios over here. 1, 2, 3, 4, 5, 6, 7, 8, 9 out of 16, that's that guy. I've got 3 out of 16, 1, 2, 3, which is that guy. I've got 3 out of 16, which is that guy, and 1 out of 16, which is that guy. So you can choose either approach, it will get you the same answers. either a jumbo square or two separate where you multiply the fractions. So continuing on, again, I'd pause, try to do it on your own, and then take a look at what I've come up with. In this example, I've got a female who's heterozygous for eye color, so she's heterozygous for E, and she's heterozygous for pigment color. And she is bred with a dog who is homozygous light-eyed, which is recessive, and heterozygous for pigment. So those are my parents, mom and dad. I now want to know what is the phenotypic ratio of the offspring. Personally, I am going to do the two square approach. So I'm going to draw a square for eye color. And I'm going to draw a square for pigment color. I never imagine them in my head, I draw them. And I want to know how many will be dark-eyed and dominant foot color. So that's option number 1. How many are dark-eyed and pink pigment? How many will be light-eyed and black? And then how many will be light and pink? So those are my 4 options. So I'm ready to now find my fractions and multiply. So how many are going to be dominant would be 2 out of 4. How many are recessive for E would be 2 out of 4. How many will be dominant for N is 3 out of 4. And how many are recessive for N is 1 out of 4. So I'm now ready to multiply and solve. 2 times 3 is 6 out of 16. 2 times 1 is 2 out of 16. 2 times 3, 6 out of 16. 2 times 1, 2 out of 16. If you drew a giant Punnett square, you should get the exact same ratios. So my ratio is 6 to 2 to 6 to 2. I can simplify that because all of those values there can be divided by 2. So if I divide all those values by 2, I'll get my final ratio, which is this. The order doesn't really matter because in Mendel questions for AP, they're pretty much multiple choice. So you would not see an option that contains those same digits in a different order. Lastly, number 4, if 4 puppies are born, how many would have pink pigmentation? If you have your giant Punnett square drawn, you can just count them up. How many will be little n, or I can look at my square here. How many will be little n would be 1 out of 4. So if I've got 4 puppies, 1 out of 4 of them will be pink, so that answer is 1. How many would be pink? 1. 1 would be pink. Next is incomplete dominance. Incomplete dominance is generally a simple mini little Punnett square. So in incomplete dominance, we see that the heterozygote has an in-between phenotype, meaning I don't clearly see the dominant and I don't clearly see the recessive, but rather I see this third phenotype that is somewhere in the middle. An example of this in flower color. Those that are homozygous dominant are red, those that are homozygous recessive are white, and those that are heterozygous are neither red nor white, but rather they seem to be a blend of the two, which when red is mixed with white produces pink. So it's this intermediate phenotype. Here is another example of cholesterol. People who are homozygous dominant are normal. People who are homozygous recessive have 5 times the amount of cholesterol, and then I see a third possible phenotype, which is neither normal nor 5 times, but rather it's about halfway between with about 2 times the amount of cholesterol. So to do some practice again, I would try to pause it, answer them, and then watch to see how you did. So I can identify that I'm looking at an incomplete dominant question because the heterozygote is neither dominant nor recessive, but rather it's halfway between, coarse-haired. So I've got this coarse-haired guinea pig, so he's going to be heterozygous, mated with a smooth-haired. Smooth-haired, it tells me above, is recessive. So I've got my Punnett square. I would always draw them. And I'm being asked what fraction will be coarse-haired. My coarse-haired are those that are heterozygous, so that would be those two. So I've got 2 out of 4, which simplifies to 1 out of 2. Question number 2, if I have 2 coarse-haired, so I've got 2 that are heterozygous and they are bred, I am then asked what is the phenotypic ratio. So I'm going to figure out how many are wired-haired. Wired-haired would be 1. How many are coarse-haired would be 2. And how many are smooth-haired would be 1. So my ratio should be 1 to 2 to 1. Codominance is sort of similar to incomplete dominance in that the heterozygote shows a third phenotype. However, different than incomplete dominance, in codominance, my heterozygote has both traits. So incomplete dominance is a mix where I see an intermediate, but in codominance I can clearly see parts of the dominant and parts of the recessive. Another example of this is these chickens. These chickens can be white, they can be black, or they can have some white and some black feathers, and I call that codominance because I clearly see parts on the chicken that are black, and I clearly see parts that are white. A third example of this is in cows. Cows can be what they call red, they can be white, or they can be this intermediate, which they call roan. Roan has patches of red fur and patches of white fur. So let's try an example. This is about the cows. If I have a brown cow and it is mated to a white bull, my intermediates will be neither red nor white, but they will be what I call roan. So what fraction will be roan? All of them, 4 out of 4, which is 1 over 1, which is 1. All of them will be roan. An example of this is blood type. In blood type, A and B are codominant, but O is recessive. You may recall hearing about blood type when we did the immune system unit. But in blood types, we are talking about the sugars, the epitopes on the outside of the cell. People who are blood type A have a particular sugar, which in this diagram is represented as a circle. People with blood type B have a different sugar, which is represented by a square. People who are AB are codominant, and thus they have both circles and squares. I see some A and some B epitopes. People who are O have neither, and O is always recessive. In blood typing questions, I can use 2 different lettering methods, and there's really not one that's better than the other, but I personally prefer the right column simply because it's less writing for me to do. So what this chart says is that people who are blood type A could be homozygous A, or they could be heterozygous and have that recessive O as well. People who are blood type B can be homozygous B, or they could be heterozygous B because they have that recessive O. People who are blood type AB must have both an A and a B, and people who are blood type O are recessive, so they have OO. Let's try some examples. A man is type O, there he is, and the woman is AB. I'm going to quickly fill in my square. And I see that half of mine are heterozygous A and half of my offspring are heterozygous B. Question 4 is asking me what's the chance that they will be blood type A. These kids here are blood type A, so I have 2 out of 4, which simplifies to a half. Number 5, a man and a wife are both heterozygous A, so they are carrying that recessive O around. And what percent will be type O? I can see that I've got 1 out of 4 here that will be type O. This question, I guess, technically is asking me for a percent, so that would be 25%. Another couple examples. Question 6. Man who has blood type B. Well, I'm not quite sure if he is homozygous or he is heterozygous, so I'm going to put a little question mark there. That could be a big B, or it could be an O. And he marries a woman who is homozygous A. What are all the possible blood types of their children? Well, they definitely could have kids who are AB. If this particular dad was homozygous B, then these kids would also be type AB. But if this dad was heterozygous, then those kids would be type A blood. So I'm going to have 2 answers for that, which is type AB or type A. Specifically, it would be heterozygous type A. Question 7, a woman gives birth to a baby who is type O. So right off the bat, I know they had to get an O from mom and they had to get an O from dad. She's not too sure which of the 2 men is the father, so she's got one candidate who's type AB. Well, that candidate could give an A to his kids or give a B to his kids. He cannot give an O to his kids. So I know automatically that Jim Bob there is not the father. To confirm, this other guy is type B. He could possibly have an O. So Jim Bob would be not the father. The father has to be the other guy who's type B. The next idea is sex-linked genes. Sex-linked genes are those that are on the sex chromosomes. In humans, we denote females as having 2 X chromosomes and males as having 1 X and 1 Y. As you can see, the X chromosome is much larger in size and in the number of genes that are on it. Therefore, most sex-linked genes in humans are on the X chromosome, simply because the Y chromosome doesn't have nearly as many genes. Usually, when we talk about sex-linked genes, we're talking about recessive genes. So therefore, a female could be homozygous dominant, a female could be heterozygous, or a female could be homozygous recessive. If I'm looking at a recessive trait, then these 2 genotypes on the top would both show the dominant trait, which is usually considered like the healthier trait, and then the homozygous recessive individual would be the only way to show the recessive phenotype. However, in males, there's only 2 options because we do not put the trait on the Y chromosome because the trait is not carried on the Y chromosome. So therefore, in males, they're either straight up dominant or recessive, and there is no male who is a carrier because it is impossible for the male to be heterozygous. Because of this fact, where the male is going to essentially either get the trait or not, we tend to see that these particular traits show up mostly in males. Color blindness is an example. Hemophilia is a blood disorder where your blood doesn't clot. And also, this one particular form of muscular dystrophy is an example. But in sex-linked disorders, they tend to be mostly in males. So when I look at a pedigree, if I see that almost everybody or everybody affected is a male, that tends to lead me to conclude that it is a sex-linked trait. If I see equal representation in males and females, I would say that it is an autosomal trait. So now a little bit of practice. Again, I would pause, try them, and then check. Number 8, a healthy man marries a woman who's a carrier. So my healthy male, I don't put a letter on the Y, and my female is a carrier, and I'm going to fill out that Punnett square. In my Punnett square, I can see that half of my offspring are male and the other half are female. And I can also start to identify who has this trait and who doesn't. Question number 8 is asking me what percent of their sons will have hemophilia. So when I'm looking at their sons only, what percent would have hemophilia? Those would be 50% of the sons would have hemophilia. Of their daughters, what percent would have hemophilia? None of them have hemophilia. So again, this illustrates that these sex-linked traits tend to show up in males more often. Question number 9, a healthy woman marries a hemophiliac male. So I'm going to start with my male, hemophiliac. My woman is healthy. I don't know that I'm really given enough information to know what is on that other X chromosome. So I have a little bit of an unknown situation here. My firstborn kid has hemophilia. So one of these kids here in my Punnett square has to have hemophilia. That Y doesn't look so good. Okay, so how do I get a kid with hemophilia? Well, these kids are healthy. So one of these kids or both of these kids would have hemophilia. So that means that this here has to be recessive. So my mother has to have a recessive allele in order to have any kids that have hemophilia. Question 10. What are all of the possible genotypes and phenotypes of males? Well, I know my males are XY. So I could, in this particular case of cats, have either a dominant or a recessive on the X, meaning my male could be orange or my male could be black. Question 11, an orange female mates with a black male. And I am asked what fraction of the females, so I only care about the females, so I'm only going to look here. So what fraction of the females would be tortoise shell? Well, I've got one that is tortoise shell here and another one. They both will. So 2 out of 2 would be tortoise shell of the females. So I can simplify that.